Okay, hello and how are you? Welcome to this tutorial. Nature handling topic number 39 according to our physics curriculum, which is basically photoelectric effect. And I'm your tutor, Dick Joseph Adeli. Before we begin, I pray that you may bow down for word of prayer. Father, Lord in heaven, we invite in this session that you may be able to guide us in everything that we do. You being the greatest physicist, I pray that you may teach us photoelectric effect for the glory and honor of your name. Jesus, I may pray. Amen. First of all, specific objectives, because we need to be able to know the place we are headed to and what we need to achieve by the end of everything, as we shall be wrapping up the topic, because it's not good to be able to learn something out of the woods unless it's a leisure time. So by the end of this topic, you should be able to perform and describe simple experiments to illustrate the photoelectric effect, which is basically what you're going to virtually handle in this particular tutorial. You're not going to practically do it, but it's something that it can be done provided the apparatus are available and you can be able to conduct it. It's no big threat, but I shall do the summary here on this particular tutorial so that you're able to understand what is required of you in performing and describing simple experiments to illustrate the photoelectric effect. So I pardon me for that. In upcoming tutorials, we shall be able to explain the factors affecting photoelectric emission. You should be able also to apply the equation E is equals to HF to calculate the energy photons. We shall also explain what energy photons are. With the time, we shall be able to acquaint ourselves with the meaning of this particular equation, which is basically, it means energy E is equals to H. We shall be able to define H in time and be able to know that it's something called Planck's constant, and F is basically the frequency of the particular radiation that is being used. We shall be able to explain all these particular terms, and photons we shall be able also to know that energy in light, we have discrete amounts and we measure the light energy in form of photons. All that shall be able to be explained in time. We should be able also to define threshold frequency and work function and electron volt. I believe the term threshold frequency and work function are not new terms, and also electron volt, I suppose from chemistry, should also not be a very new term. You know that threshold frequency, it relates to the amount of frequency that is required to eject an electron from the metal surface. We shall be able to explain all this, whereby we shall be able to know that threshold frequency is basically the minimum frequency that is required to be able to eject an electron. And from threshold frequency, we can be able also to know that there's another term known as threshold wavelength, of which we know that that is basically the maximum amount of wavelength of a particular radiation that is required to eject an electron. Work function is also another new term. All this we believe we covered that in cathode rays, and you are not badly off. If not, please go check out that tutorial so that you're able to acquaint yourself with this. Work function, whereby we said the work function is basically the minimum amount of energy needed to dislodge an electron from a metal surface. So the only new term that is remaining here is what we term as an electron volt. So that you don't remain in the blues for long, the electron volt is basically a particular constant. Okay, let me not say a constant, but it's basically the amount of voltage that is in the particular in the number of electrons that you are given. Basically, that's how I can be able to give you as a definition just for this particular case, But as we go along, we shall be able to understand clearly what the electron volt is. Basically, it's a kind of a unit of which it's a product of the number of electrons and the voltage on each electron. Basically, with time, you can be able to know that the if you have the electron charge and the electron volt, you can be able to calculate that, and you'll notice that with time you can be able also to find that electron volt will also be equated in a particular format from what we call Einstein's equation. So don't be worried of all this. And then this brings us to the next statement, of which we should be able to explain photoelectric emission using Einstein's equation. So that also shall be covered by the end of this topic. Should be able to explain that, and then finally explain the applications of photoelectric effect. Fine, let's now dig deep into our tutorial. This will be quite a shorter one because it's basically with introduction, basically laying grounds for everything. So let's get in. Oh, I forgot one: solving numerical problems involving photoelectric emission. That's something that you should never forget. Now, we spoke of some new terms. Let's now explain what they are. If you have a metal surface, or basically let me start from a far way behind. We explained about cathode rays, and we said that cathode rays are produced by when a particular metal surface is heated well enough to be able to reach the work function. You'll find that electrons are dislodged from the cathode towards the anode if there's an electromagnetic field. Now from that, we can be able now to know that there is a form of energy that can dislodge electrons from the metal surface. But now, if we don't utilize heat energy, there's also one more type of ways of dislodging the electron that we need to also to know and that one is what we call photoelectric effect. This is whereby you have electromagnetic radiation striking a metal surface and dislodging an electron. But that before an electron is dislodged, there are a number of parameters, or basically conditions, that ought to be met so that that electron is dislodged from the metal surface. And those particular conditions is what we termed as work function. Work function, we have the threshold frequency and the threshold wavelength. All of them must be met, and we know that if we have the threshold frequency, basically if I get the inverse of it, I'll have a threshold wavelength. So that is no big deal according to mathematics. So what we need to know is that if I have an electromagnetic radiation that is of work function is of let me say the work function is matching the one for that particular metal, or its frequency, it will be able to dislodge an electron from the metal surface. Now, when the electromagnetic radiation of sufficient frequency is radiated on a metal surface, electrons are emitted. These electrons are what we term as photoelectrons, and basically the phenomenon in which that photoelectric effect occurs, that particular process occurs, is what we term as photoelectric effect. Now let's basically explain what we mean. So if I have radiations, for example UV radiations, what will you observe? So here I have my electromagnetic radiation source. When it strikes the metal surface, we'll have electrons ejected. So that's what basically will happen, and we have spoken of some very good two terms, photoelectrons and photoelectric effect. Let's get down to explain what these two terms are. Now let's begin with photoelectron. Photoelectron is an electron ejected from the surface of a material by photoelectric effect. But it's also good to understand the background of what photoelectric effect is. Photoelectric effect is the emission of electrons from the surface of a metal following the absorption of electromagnetic radiation. That's what basically photoelectric effect and photoelectron are. Please acquaint yourself with those definitions because they are very, very important in our study, because the moment you understand the definition, everything falls into place and you can be able to understand what clearly we are dealing with. Let's get to our first experiment. Now this experiment, you can find it in your textbooks. Experiment 9.9, the first part, we have using neutral plates. Now here we have our diagram, our experimental setup, of which it's made of a cell. So we have a DC source here. We have a galvanometer. We have here two plates labeled B and labeled A. Now we need also to notice the convention in which they have been connected. We notice that in the first case we have the positive side and the negative side and all that. I believe you can notice the conventions. So the moment we have the anode connected to be the plate B, B also becomes like a part of the anode. It becomes positively charged, and A becomes negatively charged because it connects with the negative electrode. So basically this is the arrangement of everything. We must have two plates labeled A and B. We also have to have here we have a galvanometer, and then we have here a source. So basically, if I have my UV radiation, for example, it's a type of electromagnetic radiations. It's basically ultraviolet, for example. So if they strike this metal A and they have sufficient frequency, electrons shall be dislodged in that direction towards B, because there's an electromagnetic field here. So that's what basically will happen. And the moment these electrons will flow towards B, there's something that shall be noted at this galvanometer. So the moment there's that, the galvanometer shall be able to move, or shall be able to, what can I say, there shall be a deflection on the galvanometer. It shall be able to deflect. But now here comes another thing. What if I now introduce a barrier here, for example a glass barrier? If I introduce a glass barrier between B and A, there shall be no deflection noted on this galvanometer. Reason being, the radiation has been stopped. So basically an explanation to this should be able to know is that when ultraviolet radiation energy falls on a metal surface, some electrons absorb this energy and are dislodged from the surface. The deflection of the galvanometer indicates that electrons are emitted at plate A and attracted by plate B, causing a current to flow. I believe you should be able to notice that because it's negatively connected, this is the cathode, there shall be electrons released or dislodged, and they go towards B, and electric current flows in the opposite direction from B towards A. I believe you know that from current electricity. Something else you need to know, that the glass plate, however, easily stops the ultraviolet radiations. So it stops that. But basically you have a radiation like, for example, gamma rays, X-rays, those have high penetrating power, they shall be able to go through. So here we have UV radiations. So if I have a glass block here, there shall be no deflection on the galvanometer. But notice, I don't want you to cram that this will be the direction of the galvanometer. It can also deflect in other ways. You'll find that when the UV radiation strike there, electrons are dislodged. Basically, we'll find that the deflection can be in any direction. So basically, let me have this final slide to be able to explain clearly what we basically mean. They dislodge, and basically it can be near either side depending with your connection of the galvanometer. Basically, if you connected them in a particular convention, find that it deflects in different ways. The main thing is that it's a deflection that occurs. The direction does not matter here. If there's a deflection, there shall be an indication that there's a current flow. And basically, if this that glass block, the UV radiation cannot penetrate the glass block or the barrier. Let us get to the second part of our experiment, in which we are now going to use a charged electroscope to be able to understand of what photoelectric effect is. Here with us, we have various components that we need to be able to get acquainted with. So in this experiment, we are demonstrating still photoelectric effect, and with us, we have a gold leaf electroscope, an ultraviolet lamp, and we also have a zinc plate. So here is the lamp, the ultraviolet lamp. Here we have the zinc plate, and here we have the charged electroscope. What we are going to focus on two ways in which the electroscope is charged, both negatively and positively. We are beginning here with the positively charged electroscope. So if I bring my lamp here and then light it up, the moment it's lit there and it has been heated up to a particular way, that's not very important explanation, but it's good to be able to know that it usually heats up. So after it's heated up to the required heat, there is radiation that is UV radiation that is emitted, and once it's emitted, there's a process that shall follow. There's the dislodging of electrons. But notice, in this case, we have a positively charged plate. Basically, when this is something you need to note, when the zinc plate is irradiated with ultraviolet electrons, there's something that shall occur. Let me begin by giving you what shall be the observation here before we get into the explanation. Basically, for the positively charged electroscope, the lever, however, remains the same. It doesn't fall, or doesn't the divergence doesn't increase. It basically remains the same, or it doesn't reduce. It remains the same. So this is because when the zinc plate is irradiated with ultraviolet radiations, electrons are emitted from its surface. That's something you need to be able to appreciate that. And the photoelectric effect, the photoelectrons emitted from the positively charged zinc plate do not escape due to the attraction by the positive charge on the plate, and the leaf divergence therefore remains the same. So that's something you need to be able to appreciate. So because of the force of attraction that is caused by the positively charged electroscope, the electrons are not emitted. Therefore, the divergence remains the same. Let's get to the next experiment, of which now we have a negatively charged electroscope. We light up our UV source. The moment it has reached its optimum, producing a point of giving us the UV radiations, they shall be ejected. Once they're ejected, there's something you shall note. Because this is a negatively charged electroscope and we have a negatively charged zinc plate, the moment the sufficient frequency where UV radiation strikes the metal surface, the electrons shall be ejected and they shall be repelled by this particular electroscope. Once they are repelled, we'll notice something with the divergence, because the number of electrons are reducing. Since they are reducing, now we find that it's kind of balance of the positive charges and the negative charges, so the divergence reduces. Let's get a more factual explanation to that. However, for the negatively charged electroscope, the leaf divergence decreases. So this is because the electrons emitted from the negatively charged zinc plate are repelled and the electroscope becomes discharged as a result, which the leaf divergence decreases. That's something we need to be able to appreciate. So the leaf divergence decreases, as you have seen there. So if a sheet of ordinary glass which absorbs ultraviolet radiation, as we saw earlier, is introduced between the negatively charged zinc plate and the ultraviolet source. The lead divergence remains the same. This is for both of them. We didn't bring it up in the positive electroscope because the divergence just still remains the same. So we cannot be able to notice a very good difference. But for here, because it decreases at first before introduction of the glass barrier, when you introduce it, the divergence still remains the same because there is hindrance of the UV radiations reaching the zinc plate. So that's basically a very good introductory start that we can be able to have. So in the upcoming tutorial, we shall now dwell into the next subtopic of the tutorials, which is light energy and quantum theory, which is very, very interesting. I assure you that this is very interesting for us to be able to look at. Please don't miss it out, whereby we shall now start looking at Planck's constant and the formula E is equals to hf, play around with Einstein's equation and be able to understand all those things, work function, threshold frequency, apply them in calculations. Otherwise, success in your preparations, and may God bless you abundantly.